Somehow, I managed to miss an important, but quiet revolution that has occurred, in the field of lighting technology. Today, I am going to fix that oversight. This is a flashlight made using a technology called, laser excited phosphor. Or just, LEP for short. In this video, we are going to figure out how this thing works, test how far it can throw a beam of light, and measure its actual optical power output. First of all, we need to make it clear that this is not a product review video. This video is not sponsored, and that we purchased this product for ourselves. This is a video about LEP flashlights in general, but the device we are testing is the TrustFire T30R. This isn't the product with the best specification, nor is it the cheapest one we could find. It was a sort of compromise between cost and performance. We got this thing on Taobao and it cost a whopping $90. As flashlights go, these things are bloody expensive. So, don't expect us to be too brave in the teardown, we just can't afford to break stuff like this on a whim. But, we are going to attempt a number of interesting techniques, to try and measure the optical output power of this insanely bright flashlight. We also want to find out, if this is a genuinely useful product, or if it is just an interesting, but overpriced, toy. Let's start, by taking a look at exactly how this piece of technology actually works, and why it is possible to have such a bright and tight beam of light, from such a small flashlight. So, I guess we should talk a bit about how this rather impressive flashlight actually works. Ironically, the optical chain is almost the same as for a typical white LED, but this one is on steroids. At the heart of the device, is a blue laser diode. This is usually a 450 nanometer diode, like this one. Using a laser offers a couple of major advantages. Firstly, due to it being nearly an ideal point source, it can be focused to a much smaller spot size. At the small focal point of the laser, there is a special crystal, which will fluoresce. This crystal is made of a material called cerium-doped YAG, and when it is excited by the 450 nanometer blue laser light, it will release a partial spectrum of colors, from green to red. To our eyes, this, in combination with the blue from the laser, will appear as a white-colored beam of light. And because this is an almost ideal point source of light, the final collimation of the beam is also far better than for a normal LED-type flashlight. The second advantage of using a laser, is the higher optical power output, which obviously helps to make this a very impressive source of light. This is a very low power, 450 nanometer, blue laser pointer. And this is a vial containing the same compound that is used to make white LEDs. As you can see, it has a very impressive white glow when the blue laser excites it. This is a small white surface mount LED, that we removed from a cheap flashlight. It's quite a nice magic trick, to be able to light these up without any power. In fact, any white LEDs can be stimulated to light up in this way, assuming you have the correct laser wavelength. In fact, even a complete flashlight can be made to emit white light, when hit with a blue laser. Anyway, now we are going to test how far this flashlight can actually throw a beam of light. The first thing we need to do, is to identify some clear targets to aim this flashlight at. So, let's take a quick look what we are going to be pointing this at. This wall looks like a suitable target, for a relatively close-in illumination test. We used one of those cheap laser range finders to measure the distance. It was a real pain in the ass to get the smartphone aligned with the range finder, but you can see that our wall is just over 160 meters away. Now what we need is a long-range target to illuminate. This needs to be far enough away to be a good test, but without exceeding the 1000-meter limit of the range finder. And this building looks ideal. There is golf netting in the way, but hopefully that won't matter. The range is just over 900 meters, which is ideal for this kind of test. Frankly, it seems pretty inconceivable that such a small flashlight will actually be able to visibly illuminate this building, but let's see. We are strong believers in the principle of the 6 Ps. Which means, planning and preparation prevents a piss-poor performance. So, we did some reconnaissance of the target building, making sure that we were not going to attract too much unwanted attention to our little experiment. By the standards of this city, it's a pretty low-rise building. The building looks quite reflective, but the albedo is not really as high as it first seems. These holes in the cladding will only serve to reduce the amount of reflections we can expect. This practice run also allowed us to test our communications equipment.
Local 1, this is Eagles Nest. I copy.
Although, I'm not sure everyone understood the concept of radio silence. So now we just need to wait for darkness, or at least what passes for darkness, in a city of 22 million people. Right, let's take a look at our flashlights in operation. This first one is a basic fixed focus LED type. And it clearly illuminates this wall at a distance of 160 meters. Next we have an LED flashlight with an adjustable focus. The beam has a well-defined edge and it is brighter than the previous one. But, let's see how it compares with the LEP flashlight. Well, there really is just no comparison. This light is orders of magnitude brighter than our other flashlights. It even illuminates the humidity in the air, and projects a very tight beam of light. Looking at these results side by side, the traditional LED flashlights really do seem pretty puny in comparison to this thing. Okay, so now let's try our long-range illumination test. My human assistant traveled by e-bike over to the target building, and his children are going to be shining the LEP flashlight from 900 meters away. Let's see if the marketing claims are true. Well, the illumination is certainly visible on the building, but the beam has diverged to about 20 meters in diameter, so the reflected illumination is pretty dim. That said, I was quite surprised that it was even visible at all. I guess that the first measurement we make should be of the total input electrical power to this flashlight. For this we are going to power the device directly from a DC power supply. We have already validated this power supply's displayed voltage and current, and it's pretty accurate. This device draws about 8.8 watts of total electrical power. Now, we are going to measure the relative luminescent flux from this flashlight. We are using a simple, homemade light level meter for this measurement. We will measure this LEP flashlight against a traditional LED type. This LED flashlight is the brightest one we own, so it will be interesting to see how it compares. We are testing the brightness at point-blank range, and have adjusted the neutral density filters in the meter to match. We get a measurement of 20 microamps on our simple instrument. Our LEP flashlight gives us a reading of 47 microamps, so 2¼ times brighter. Some of the viewers might recognize this light level meter from a video we made about yellow fog lamps. And yes, this is our fogometer. This wonderful piece of equipment is called a Crookes radiometer. It rotates in the presence of reasonably strong lighting. The brighter the light source, the faster it rotates. So, we wondered if we could use this as a simple optical power measurement device. First, we will calibrate it with a laser. And, we will measure the optical power of our calibration laser source. This cheap little laser power meter takes quite a long time to get a steady state reading, but it does work in a very interesting way. If you would like to know more about how it works, you could always watch our video about this interesting little device. This laser power measurement stabilizes at around 650 milliwatts. As you can see, we clearly cannot use a standard camera to measure the rotation rate of the vanes of the radiometer. We will require the use of a high-speed camera. You can see that with the standard YouTube video rate of 24 frames per second, the vanes appear to be spinning backwards. Our high-speed camera isn't exactly one of those million-dollar devices you might have seen on some other YouTube channels. This one is black and white, with VGA resolution, and can capture 815 frames per second. It is, however, better than the slow-motion modes used on cell phone cameras, because it has a global shutter. So, here is our reference laser measurement. We have to use pretty strong background illumination with this camera, and the resulting video is still pretty dim. From the standard camera footage, and even with the naked eye, it is not really obvious which of these light sources resulted in the fastest rotation rate. But looking at the high-speed footage, we can calculate the rotation rate based upon the number of video frames per complete rotation. And, for the reference laser, we get a rotational speed of 174 revolutions per minute, with a laser power of 650 milliwatts. With the LEP flashlight, we can see that the rotation rate is higher, about 324 RPM. If we just consider the ratio of the energy contained within the rotating vanes, then we can calculate the total power from the LEP flashlight as being about 2.2 watts. However, there are a lot of variables that have not been considered in this simple analysis, and this figure is probably an overestimation of the optical power output. Next, we are going to try and measure the optical power output using some of the measurement features of this spectrometer. And we are going to need to use some of this neutral density filter film. This flashlight is just too powerful, and will saturate the spectrometer. This neutral density film has a specification of OD1, which means that only 10% of the light will pass through it. Here in this footage, the camera is saturating, so the difference doesn't look that much. Because the spectrometer reports luminescence in units of watts per unit area, we should be able to extract a power measurement using this device. However, the beam is larger than the diameter of the input aperture of the spectrometer, and it does not have an isotropic beam profile. Here you can see that it is clearly brighter in the center. But we did get kind of lucky. The input aperture of our spectrometer is almost exactly half the diameter of the output aperture of the flashlight. And this means that if we position the flashlight correctly, the spectrometer will be able to see some proportion of all of the intensities present in the beam profile. However, this intensity information won't necessarily be in the correct proportions. So, let's see what this spectrometer makes of this flashlight. The laser that is exciting the phosphor appears to be a 453 nanometer type. And, if we look at the radiant intensity, we get a figure of about 230 watts per square meter. If we scale that for the size of the flashlight aperture, and account for the neutral density filter, then we get a total optical power output of 1.04 watts. we figured that we would just try and directly measure the output power of this flashlight, using our cheap laser power meter. The optical aperture is only 13 mm in diameter, so we can try the same trick as we used with the spectrometer. With a reading of about 320 milliwatts on the laser power meter, we can calculate that the total optical power output should be 1.09 watts. We waited until we had finished all of the testing, before we performed a product teardown. Once we had done that, we realized that we could retest the optical power, as the raw optical module was actually small enough to fit within the aperture of the power meter. So, let's try that measurement again, and see how accurate our earlier estimate actually was. This laser power meter uses a Peltier effect device as the sensor, and without the heatsink, this optical module gets quite hot. That meant we needed to be careful, not to let the optical module touch the Peltier device. Now, we get a direct measurement of 1 watt, which is in the same ballpark as our last 2 measurement attempts. And with that, let's move on to the teardown. Given that we bought this rather expensive flashlight ourselves, we saved the teardown until the very end. We just have too much experience with destroying interesting stuff during product teardowns. This device uses a standard 18650 lithium-ion battery, and it can be removed by unscrewing the combined battery cover and power switch. The battery holder itself is also very easy to remove, and it is just an aluminium tube with threaded ends. Then, there is the front lens retaining ring. We needed to use pipe grips to loosen this up, to allow it to be unscrewed. Off camera, we had to resort to this kind of brute force, in a couple of other places too. There is a glass window on the front of the flashlight, that appears to have a dichroic filter coating applied to it. From our simple measurements, this appears to just slightly attenuate the 450 nanometers laser wavelength. Underneath this window, is an O-ring to seal the optics module, and behind that, there is a spacer and the main focusing lens. This lens is pretty much the same as you will find in any other projection type LED flashlight. Now we are going to unscrew the electronics module from the optics unit. This took a lot of brute force to loosen up, and we did damage the outer enclosure in the process. On top of the electronics module, you can see one of the PCBs. This one is for charging the battery and also has pogo pins to connect to the optics unit. On the back of the optics unit, there are slip rings to carry the power to the laser diode. And on the front, we can see the tiny fluorescent crystal that allows this flashlight to produce a sort of white color. It is clear that this thing is not designed with user servicing in mind, and it is pretty fiddly to take apart. We were hoping to strip this down, to be able to expose the blue laser diode itself, but that would have certainly resulted in this flashlight being destroyed. So, in the end we just stripped this down as far as we dared. You can see the laser diode enclosure is made from a slug of copper. This thing gets pretty hot in operation and needs a lot of passive cooling. So, we can see that this flashlight is broken down into 4 main sections: the optics unit, the electronics module, the battery compartment and the power switch parts. And, that's about it for this teardown. So, now we have had a few weeks to test this device, and to use it in everyday life. What is our opinion of this rather remarkable type of flashlight? Well, It basically does what it claims. It can sort of throw a beam to about 1 kilometer. It does have a very bright and well collimated beam, and the light output capabilities are pretty overwhelming. In fact, that is mostly the problem with this thing. You see, it really isn't a very practical device. Here you can see a comparison with our brightest LED type flashlight. At the sort of distances that one might normally use a light like this, the brightness just drowns out everything that is illuminated by it. And at long distances, all that can be seen is the beam itself. And, unless you actually bolt this thing to a telescope, you won't be able to see anything useful at all. And then, we have the pretty terrible power efficiency of this thing. Whilst this device can deliver about 1 watt of optical power, which is pretty impressive, it draws nearly 9 watts from the battery. This isn't one of those flashlights that I would take out on a camping trip. Well, unless I wanted to use it to scare away dangerous animals. So where exactly is all that energy being lost? If we look at the device in operation, using a thermal camera, we can see that most of this is being dissipated in the optics unit, so being lost in the laser diode and the fluorescent YAG crystal. There is also a surprising amount being wasted in the electronics module. Okay, so it isn't a very practical flashlight, it is incredibly expensive, and it has the energy footprint of a small European country, but, it has to be said, this thing is a lot of fun to use. So, yes, it is wasteful, and probably a bit irresponsible too. But, we don't regret buying it at all. Anyway, that's all we have for you today. We hope you enjoyed our little video, or at least found some parts of it interesting. If you think we deserve it, then please feel free to give it a like. And you could always hit subscribe, if you want to see more content like this. In a change from our normal practice, we have enabled YouTube advertising. We are saving up for a camera. All of the photography you have seen in our videos has been captured using a cell phone, the limitations of which is starting to limit the kind of content we can produce. We wish to express our sincerest gratitude to the following viewers for their donations towards our camera fund. This is still a hobby channel, so we can say what we want, and YouTube's algorithm can go and get f***ed. Thank you for your time. You now have only a very short time to choose the next video to watch.